Let's start with this. Right, Niharika. Right on. So this thing can be written as, so this is a R, which is 100 ohms. This will be minus 100 J. Capacitance and inductance is plus 200 J. So Z1 is 100. Z2 will be 100 J. And both are in parallel. So Z equivalent will be Z1, Z2 by Z1 plus Z2. That turns out to be 100 into 1 plus J by 100 into 100 J by 100 plus 100 J. 100 will cancel off. Then this will be J into 1 minus J by 1 minus J square. I think that will come out to be 50, 1 plus J. Anyway, you just want the magnitude anyway. So mod Z will be 50 root 2. IRMS will be VRMS. See, the number 200 is given, means it's an RMS value. Which is 200 by 50 root 2. 2 root 2. So effective current is basically RMS. Clear with this? And this thing will be VRMS. I told you, you see an AC ka symbol and they're giving a constant number. They're talking about RMS values. Any doubts on this? Let's get this. An AC source of angular frequency omega is fed across a resistor and a capacitor in series. So it's an RC circuit. The registered current is I. So basically, this is XC, this is R. XC is nothing but 1 by omega C. So impedance will be root over R square plus X square. And you're getting V is equal to root over R square plus XC square. Now you're saying you're going to change the frequency to omega by 3. So if omega becomes omega by 3, this X becomes 3X. That means your new impedance will become root over R square plus 9X square. And he's saying the current now becomes half. And then just substitute V ka value here. VV goes off, square it on both sides, 4 into R square plus X square. Clear? Check it out. So when omega becomes 1 by 3, X becomes 3X. So it's X square, so 9X square. This is what I was saying. Main cell questions will be like this only. It's all formula based. You know the formulas, keep substituting and solving. Clear with this? And like I said, how do you know it is a normal thing? Look at this. If it is an RLC series circuit, use your regular formulas. If they ask you something as function of time t, or they give you something in parallel, go back to the complex numbers. Clear with this? Where is the other one? Hmm. Other scams on? Let's see. You can see the value of a current in two LCR series circuits. So he's talking about series circuits. Both are in resonance. Now, if you are in resonance, XL becomes equal to XC in each circuit. So that's omega L is 1 by omega C, and omega is 1 by root LC. Now let's see the options. Both the circuits must have same value of capacitance and inductor. Not necessary. They should have same value of L into C, na? Both have same frequency because see, they're using the same sinusoidal source. Matlab the frequency is same. So same for both. So L into C must be same. L and C need not be same. Both the circuits ratio of L and C will be same. Nah, that is also wrong. Product will be same. For both the circuits, XL by XC must be, that is right. Because if XL is equal to XC, the ratio is 1, na? In resonance, XL is equal to XC. So XL by XC is 1. Now understand, XL and XC ka values are different, but the ratio is same. Both the circuits must have same impedance, not necessary. Because the impedance will be root over R square omega L minus 1 by omega C square. If your L and C are different values, then for different omegas, you have different. So only C is the answer. Is that making sense? Anyone not clear with any option here, please ask.
Sir,
Then what about the B one? Aditya.
first option, sir. So
What first option?
the capacitance and inductor, like same capacitance, same like inductance. So why isn't like the product same? दोनों circuits के लिए.
What are you talking?
Uh,
Because it is in resonance, omega must be root LC. Why does it mean both should have same L and same C?
the must have. अच्छा ठीक है. मतलब may भी लिखा होता तो सही सही होता फिर.
Uh,
हाँ.
what about B thing? Again, RLC circuit is asking about this. So we know here the current will be common because it is a series circuit. VR will be in phase. VL is perpendicular. VC is this thing. Now let's see the options. Voltage across the resistance is lagging 90 degrees by the capacitor. No, wrong. Voltage across the resistance is actually leading by 60 degrees. But he's asking for incorrect. So voltage across the capacitor is lagging by 180 across inductor. True. Because if you see VL and VC, both are 180 degrees ka angle. Voltage across the inductor is leading 90 degrees. This is right. Resistance of the circuit is equal to the reactance of the circuit. That is wrong. Because resistance of the circuit is 10 ohms. Reactance of the circuit is 0 because this is 10 and this is 10 both got cancelled. 10J minus 10J. He's asking for incorrect, so A and D is the answer. Clear with this? This is how theoretical questions will be there. Please check both the questions. Please ask me if you're confused anywhere. All clear with this? So questions will be of this sort. They're not tough, but if you don't know what you're talking about, you will go for things. So like I said, I hope everyone tried solving that easy sheet. More than the tough sheet, definitely solve that easy sheet first. That's more important because the tough things now I'm pretty confident you guys can handle most of it. Let's get this. Anyway, answers are already given, so let's try to solve. Try. I'll use 3-4 minutes. The moment you see the words XL, XC, X8, and they're asking instantaneous potential difference, is asking this function of times only. So this is not a regular one. But anyway, let's see how will you solve. First part was easy. What was the impedance? 8 plus 2j. So inductances will be plus 2j, capacitor will be minus 8j. So Z will be 8 minus 6j. So Z bar will be 10 minus 37. So they're asking for magnitude normally. So that is 10. First part is done. Next thing. What about the voltage? Voltage will be 10 that he gave in cos. So I'll keep always in sine. So 10 sine 90. But if you want to take cos as 0, no, that is also fine. But then remember, all your functions will start with cos. Okay? But anyway, we are used to sine, so we will keep it as sine. Let's not confuse ourselves. So the current in the circuit I bar will be V bar by Z bar. That will be 10 by 10. 1 angle will be 90 plus 37. Great. You want the potential difference between A and B. So I need impedance between A and B. So between A and B, the impedance is 2J minus 8J minus 6J. So ZAB will be 6 minus 90. So potential difference across AB will be current into ZAB. That would be 637. There, so potential difference across AB will be 6 sine omega t plus 37. Now read that question. That wordings are a little weird. Find the instantaneous potential difference between A and B when it is half of the voltage output from the source at this instant. Meaning, this voltage is changing from minus 10 to plus 10, right? Example, let's say when this value is 7, some random number, somewhere in the middle of the problem, when the value becomes, let's say 7, he's saying at this instant, the voltage across A and B is 7 by 2. Are you getting it? So he's saying there is a particular value of this voltage. We don't know what is that value. There is particular value of this voltage. At this voltage, the voltage across AB becomes half of that. So what is that voltage? Are you getting the question? That voltage is changing from minus 10 to plus 10. Somewhere at some particular value in this, the voltage across the source and voltage across AB will be half of the voltage of the source. So what is the voltage at that instant? So if I have to write it in an equation form, this is how it looks. So voltage across AB, he's saying is half of voltage of the source. This will be 6 sine omega t plus 37 is half of 10 cos omega t. I just wrote as omega t. Can you solve this? Find that omega t there. He's asking find VAB. So if you can find omega t and substitute that, you'll get the answer. Let's give it a try. See? So expand this sine A plus B. Solve this. I think I remember this. Tan omega t will get 7 by 24. This is 7, this is 24, and this is 25. Cos omega t will be 24 by 25. Take that and substitute that. So VAB will be pi cos omega t will get 24 by 5. That means voltage of the source is how much? 48 by 5. So that's around 9.6 volts. So when the source ka voltage is 9.6, then potential difference across AB is 4.8. So it doesn't happen at every voltage. So for different voltages, VAB will be something else. How did we get VAB? From phasors.
Magnitude 6.
What?
So the magnitude should be like 64 plus 4 under root.
Yeah.
Like, how did we? Oh, okay, got it, sir. I wrote the diagram wrong. Understood. Got it.
Clear with this? There, questions will be of this sort. So this will be an advanced question. Any doubts on this? The next thing, RLC parallel circuit. Now this technically is not there in the portion. So generally mains may they should not touch this, but advanced may they will still ask because it can be still handled. So in this case, we keep a resistance, inductance, and a capacitance. So if this is the current in the source, IS, this will be current in the resistor, current in the inductor, current in the capacitor. Now, if you look at here, all of them have same voltage. So we take V is common. So the phasor diagram which you draw, so the current in the source and this thing IR will be in phase. IL will be downward. Remember, in the voltage diagram, I is this and VL was up. So if you rotate 90 degrees, if you make the voltage common, then I will come down and I capacitor will be up. So they will get reversed. So if they ask you I source RMS, this can be written as root over IR square plus IL IC minus IL whole square. If you remember, there we wrote for voltages. V source RMS square is equal to VR square plus VL minus VC whole square. So you can play the same game here. Everything is in parallel. Now here, if you look at the impedance, it will be 1 by Z is 1 by R. All are in parallel. J into 1 by omega L minus omega C. Now remember, whenever they ask you, the circuit is in resonance. Resonance meaning the impedance, right? There'll be X becomes 0. So circuit becomes purely resistive. So 1 by omega L minus omega C is 0. There, so resonance frequency is still the same. But the catch here is the impedance becomes maximum. If you remember, in RLC series circuit, impedance becomes minimum. But here 1 by Z, na? So if this becomes minimum, then 1 by Z becomes maximum, isn't it? Inverse of it. Therefore, the current will be minimum. So if you actually plot this circuit, current versus omega graph, which we did in that quality factor and all that stuff, the current would actually be like this. This is your omega resonance and you get a minimum current. This is called a rejector circuit, meaning the particular frequency will produce the minimum current. If you remember, RLC series circuit was an acceptor circuit. A particular frequency will generate the maximum current. So you can select the particular frequency. In this case, let's say if you don't want a particular frequency, but you want everything else, then we use this thing to reject that particular frequency. So these are called rejector circuits. Clear with this? That's it. This much idea you have, like RLC series and RLC parallel. Remaining all we can handle. Any other combination, it is manageable. There. With that, we're done with the AC chapter. So do finish all the 2 sheets I sent. One is the mains ka sheet, one is the other one. And I also sent EMI ka sheets also. One is only on purely LR circuits. You can try that if you want. But again, I'm telling you, EMI, AC, rotational mechanics, wave optics, these are modern physics. These topics now are pretty important ones for modern, advanced. They can make really good questions on this. So because at a mains level, this chapter is quite easy, but most people get confused with that phasors thing only. But if you are comfortable with the complex numbers, phasors will make more sense now. So that way. Small chapter, but good one. So do finish it off. Next thing, waves. Now waves, in total, we have 3 parts. The first thing is waves on a string. Then we have waves on a sound waves. And the third part is a wave optics. So it's a little lengthy, quite a big one. So we will finish off all this in one go. And after that, we'll be left only with modern physics. So let's see. Again, overall, the chapter is not tough. As long as you know your standard formulas and the standard models, you can handle most of the questions. And the only reason chapter looks a little weird is because you need to visualize stuff. So that we will take care. As long as you can actually understand and see stuff, the chapter becomes really nice. So we will see later on as we go. I'll teach you how to destroy bridges. How can you play a guitar? So you can learn a lot of stuff with this. So waves. So before jumping into what is a wave, we need to define something. What is a disturbance? This is a word which we keep hearing, right? In the class, don't disturb, be quiet. And also, so what do you mean by disturbance? Think about it. Let's say in a class, suddenly someone starts shouting. What do we say? Arey, why are you disturbing the class? Imagine the vice versa. Let's say all of us are in a party, people are jumping and dancing, and you're sitting there quietly without doing anything. Even then, people are going to come and ask. Did you notice something there? When everyone is quiet and you're shouting, people found you are something weird. You're the odd one out. When everyone is jumping and dancing, you're sitting quietly, people think you're the odd one out. So the disturbance we define like this in a technical terms, it is simply the change in property with respect to the surroundings. Now that property can be anything. So the student shouting in the class, the property is intensity of sound. So example, if you take a bulb flickering in a room, we say it's a disturbance. But the same thing in a disco thing, right? The bulbs don't flicker, we say there's a problem with the system, isn't it? So bulb flickering, right, in a room is a disturbance. So here, what is the property that is changing? The property that is changing is intensity of light. Now, when you keep saying this property, this can be anything. It can be pressure. In sound waves, it is a pressure. It can be displacement. In a waves on a string, it is displacement. It can be density. Again, in sound waves, density also changes. Electric field, magnetic field, it doesn't matter. So for example, if you take a wave on a string, and if you're observing this one point A, so as this wave pulse travels forward, you will notice as this bump is going forward, you can see what is happening. This A is simply going up, goes to the highest point, and then comes down. So here, the property that changes is the displacement of A. Actually, it is not only A, multiple points of displacement is changing. So that's what we call as a disturbance. A disturbance is simply the fluctuation in a property with respect to the surroundings. Clear with this? Next thing, so how do we define a wave? So wave is nothing but the propagation of this disturbance. So in your class, let's say the guy in the first bench starts shouting. Then he keeps quiet, the person in the second bench shouts. Then he keeps quiet, the person in the third bench shouts. And so on. Now what do we say? We say the disturbance is propagating. वो क्रिकेट में होता है ना स्टेडियम में all people are just standing and sitting. It feels like the wave is propagating. Ever seen that? So something like that. So the propagation of this disturbance is called a wave. Getting it? So one day ask someone what is a wave, and that guy says this is a wave. I said, "Okay, if this is a wave, that means a snake is a wave." Because snake also looks like that only, na? Right? So snake propagates in space. So snake does two things. If you add a snake and a snake, you'll get four snakes. Principle of superposition. You have all that weird kind of stuff. It's called the snake wave theory. We have created it for a kid who thought the snake was this. Actually, it was not a kid also. There was one guy who came for a demo for a teacher interview long back, 2013. People had all weird things about a wave. Now, in a wave, you can also say like this. In a wave, energy and momentum are transferred without the transfer of material. So through a wave, you can send energy and momentum without any transfer of material. Or transfer of matter. So you can classify waves based on the medium. You can classify them into mechanical waves. Non-mechanical waves. What's a mechanical waves? These things require medium to travel. For example, your sound waves, they don't travel in vacuum. Waves on a string require this thing. Waves on a water cup pond, they require the water there. So in our portion, right, we'll be sticking only to waves on a string and sound waves only. And EM waves, we have a small subtopic of that only for mains level. These things do not require medium to propagate. Example, electromagnetic waves. When it's electromagnetic waves, it's a whole spectrum basically. You have light, you have X-rays, you have infrared, UV. All these are electromagnetic waves. So this is one way you can classify the waves based on whether they require medium or they don't require medium. Another classification, you can also classify waves based on the propagation of the particles. Yeah, we have a bit of a theory today. So the first one is transverse waves. So in transverse waves, the particles or the property They oscillate perpendicular to the wave propagation. Meaning, if a wave is traveling in one direction, these particles are going up and down. They're not going left and right, they're simply going up and down. And if you look at this thing, the example in the first page, this is the same example basically. So if you look at the waves on a string, look at how the particle A is going. A is simply going up and down, isn't it? As the wave is traveling forward, the A simply goes up and down. You know, where else you see this kind of thing? So if you see now the waves in a beach, or when you throw a stone into a pond, the waves which you see are actually transverse waves. That means, let's say unfortunately we got stranded in the ocean where there is no wind and there is no ocean currents. And if there are waves going on, and if you're stuck in a boat, you know what will happen? Nothing. The boat will simply go up and down. You'll not go front and back. You're stuck there forever. The reason what happens in real life, there are some ocean currents, so they will drag you, or there is a wind which will blow you away. But if you're in a part of an ocean where there is no wind currents, nothing, you're stuck. So if you actually see waves now, when the waves are coming in an ocean, you actually can't see the waves. They're like pretty normal. They have wavelengths of around 2 to 3 meters. So what you see actually the beach ka thing in the coastline, right, is something else. So if you see beaches now, there are two types. Actually, there's only one type of a beach. If you go to beaches in Goa and all, this is how the water looks like. It's a very shallow continental shelf. Matlab, there is a land for almost 1-2 kilometers. You can keep walking inside and the water only comes to your chest level. And then slowly it gradually drops. These places are very good to make beaches, right? The depth is only 3-4 meters. You can do that scuba diving and all that stuff. You must have done this, sports activities. So these are very good beaches. There's not much of a thing. Now, when a wave comes from the deep sea onto the beach, this is what happens. As this wave comes here, the front part of the wave hits the land, so it slows down. The front part is slowing down, but the back part is still traveling faster. So this wave actually climbs on top of it. It's getting compressed. As it goes forward, the front part keeps slowing down and the back part keeps climbing. The height of the wave actually increases. So how high you will go will depend on the wavelength. So if the wavelength is lambda, you reach a height of around 3 lambda by 4. There's some formula there, 0.6 lambda or something. So if you have a wavelength, a big wave, then you get a big height. If you have a small wavelength, you get a small height. And once it reaches a certain height, this will crash and then you get that splash. So when you see in a beach, right, that is what you see. But if you go to beaches in Kerala and all, right, these beaches are like, they're not beaches only, they're like this. Matlab, it just drops. Pretty sharp drop. You go like 4-5 meters and then it starts dropping. These are pretty dangerous beaches, but these are pretty good to make ports. You can get a ship very close to the coastline. Na? These things are very good places, to make harbors. So you get a very deep waters, pretty close to the coastline. Ship can come pretty close, and these are good. If you see, Kerala has around 4 ports. So those beaches are that. Now, when you get a tsunami is actually a transverse wave. So if again, what happens in a tsunami, right? You must have studied this, continental plates. So the continental plates, what will happen? They're pushing into each other, and sometimes right at certain areas, tectonic regions, these plates are going under this. So as this plate starts going pushed inside, because of the heat, it starts melting, it starts building up a lot of pressure. Now this might take decades or years or might be centuries. Now, if you're lucky, what will happen? This other continent plate will get pushed out slowly. So if it gets pushed out slowly, that itself will create big earthquakes. Unfortunately, sometimes it happens, these things will suddenly snap. The whole thing will just move with one big jerk. These things are huge earthquakes. Matlab, you get earthquakes of 8.58 and all that. This will be massive earthquakes. Now think about it. If all the water is here, and due to this pressure, if this thing suddenly snaps, what happened to all this water here? It got pushed up, isn't it? Now here, this is not a small amount of water. We are talking about a huge. It's a continental plate. So that is a reason. So when this moves, the entire earth will start shaking. We call it an earthquake. That is the reason whenever there's an earthquake, people actually start searching for if there's a tsunami. So if this snaps, all this water here will start creating a splash. It starts going on both the sides. These things have a wavelength in the range of 10 kilometers. And they travel in a speed of almost 600 to 800 kilometers per hour in the deep sea. These things are traveling with the speed of commercial flight. And when they hit the coastline, the water wave will rise to a height of almost 20 to 30 floors. If you have a building around you, 20, 30 floors, imagine how high is that. You're standing in a beach and you see a wave of 30 floors high, hitting you with a speed of 150, 200 kilometers per hour. Tsunami comes, there is no way, start running. There is nothing stopping it. Getting it? And once it hits the coastline with that speed and that kind of velocities and all, it will push into the coastline for 4 to 5 kilometers. Nothing survives. The water doesn't kill you, the debris will kill you. It will just, the car, this, everything will just start getting dragged with it. These things are deadly. Matlab, it comes, there is no way out. The only way you can survive if there is a mountain or some tall, strong structure. So even buildings are not safe. Mumbai, we don't need it. If it rains, we'll get a tsunami automatically. So we don't need all these kind of tsunamis. हमको just आधा दिन का rain चाहिए. So luckily, we don't get tsunamis here because if you see Arabian Sea does not have any continental plates, we are kind of safe. But in 2003 or 4, I don't remember, I was in school, I guess, or in college. There was a huge earthquake in Indonesia. That Malaysia, Indonesia, right? It was huge. Matlab, the entire area got destroyed literally. After destroying, it sent a tsunami. It just didn't stop with destroying with an earthquake. Unfortunately, that time we didn't have any tsunami warning systems. Japan had it, but people didn't expect anywhere else. Imagine from this Indonesia, right, Kuala Lumpur and all that, it took 4 hours for the tsunami to reach India. You know how long does it take a flight to go from Chennai to Singapore? 4 hours. This thing took 4 hours to reach. This thing was literally coming with the speed of a commercial flight, 700, 800 kilometers per hour. And no one knew it. The first people to know was Andaman Islands, the naval station which was there, that hit got by tsunami. Then they realized, shit, this is bad, and they sent a signal to Chennai. It took 1 hour to go from Andaman to Chennai. So Chennai people had only 1 hour to prepare for the tsunami. They started sounding alarms. Luckily, it is a city, though they evacuated the coast and all, but most of the villages in the south coast of Chennai, right, they literally got devastated. Meaning, when I was studying in Madras, we had people who were telling stories. Matlab, to socho na. Today morning, you enter the village, you talk to everyone. There is a school, there is a post office, there is bank, everything. Next day morning, you went there and you saw was a sand, nothing else. Gone, wiped out. There were no people, no buildings, nothing left out. There is no traces like there was a village before. And there were like almost 400, 300 villages got wiped out like that. It was horrible. So yeah, tsunamis can be dangerous. So if the other way to survive a tsunami, right? Some people did this also actually. Especially fishermen. What happens if you leave your boat in the coastline and run away? You will be safe, but your boat will get destroyed. But for the fishermen, the boat is a survival. So I saw these people doing also. I think somewhere in Europe side or somewhere, what they do now, if this is the coastline, you take your boat and go into the tsunami. The thing is, the problem tsunami becomes a problem when it hits the coastline. So if you can go into the deep sea, and if your monster tsunami is coming, what happens? The boat will simply go up and down. Na? So as the tsunami is passing, now see, it is 10 kilometer wide. First of all, you won't even realize you're on top of a tsunami. The tsunami will simply going under you. Maybe while climbing, there is some turbulence. While coming down, there is some turbulence. But you're safe. The tsunami just goes under you. So that is another safe place. Yeah, but who will have the guts to think like I'll go into the tsunami? So there, a mountain or this thing. So you can actually detect tsunamis like this only. So now we have warning systems. What they do, you know, these buoys, they keep floating in the water, oceans. So you drop these buoys every 500 meters, a lot of them in areas where you think there's a tsunami. So whenever a tsunami comes, what will happen? The buoy will go up. Okay, 1 went up, the big deal, maybe an error. 2 went up, 3 went up, 4 went up, 5 went up. That is fine. When the 6 goes up, the 1 comes down. Means what? This is the wavelength of the tsunami now. I found out how big is the tsunami, and I know at what rate these things are going up. So I know the speed of the tsunami. So at least I can tell you in how much time it will reach the coastline, and I can tell you how big is the tsunami. You can send a warning signal, and you can evacuate people. That's it. There is no other option. You can't fight it. You can't throw a nuclear bomb on it. Nothing happens. Some people had an idea. Let's throw nuclear bombs on a tsunami and stop. Bullshit. Kuch nahi hoga. A nuclear bomb, it's dangerous because of the nuclear radiation. It doesn't generate enough power. You can't stop. Anyway, so that is one. And one more precaution. You see a tsunami, it happened somewhere in Hawaiian Island side. Tsunami came, people knew, they all ran away to the mountains. Tsunami came and went away. After going away, the water was shallow and also there were a lot of fish left on the coast. People were so happy they went down to take the fish. Second tsunami came and took them all away. So sometimes tsunami comes in waves. So after seeing one, don't become, thinking like it will not come, and don't do chill out. Wait. Tsunamis normally have a time span of sometimes between them an hour. So you better wait for half a day and then you go. Anyway, so if you're stuck with a tsunami, I'm telling you, right, there's nothing. Don't you see something, don't even think that you can do some, run away. Start running as far as you can. Like I said, coastline say 5 kilometers it will hit. Matlab to soch. You have a vehicle, take it, start running. Anyway, so that is one. So next thing, longitudinal wave. In a longitudinal wave, the particles oscillate in the direction of the wave propagation. That means if a wave is traveling like this, the particles are oscillating front and back. Or the best example is your sound. Let's say if there is no sound in the atmosphere or in the air, the molecules will be equally spaced. So whenever there's a sound, what will happen? The regions get compressed, some regions get expanded. In school, you studied this thing as compressions and rarefractions. So here, if you see molecules come closer, compression and rarefaction. So this is two ways you can classify mechanical and non-mechanical. For example, see, waves on a string are mechanical because they require a string and they're transverse. Sound waves are also mechanical, they require a medium, but they're longitudinal. Electromagnetic waves are transverse, but they are non-mechanical. Are you getting it? So there is nothing like that. You can have a non-mechanical transverse wave. This is one. Next thing. So there we saw a definition of a wave and we saw types of the waves. So if you want to study waves, we need to define certain properties. So there are three properties for a wave. If you know these three properties, you know everything about the wave. For example, if you want to find the motion of a particle, what all things you need? You need the initial position, you need the velocity, you need the acceleration, isn't it? If I know these three things, I can get everything you want. I can tell you where will it be in some time. I can tell you the velocity, I can tell you everything. Similarly here, there are three quantities which are required to study a wave. The first thing is frequency. The symbol is F. Same thing, it's the number of oscillations per second or number of waves per second. This is the same thing that you learned in SHM. So frequency depends on the source and independent of the medium. Let's say you're shouting 3 times per second. It doesn't matter whether I keep you in a room or throw you under the water. You'll still shout 3 times per second. So the medium has nothing to do with how many waves you are generating. It depends on the source. I know, bad example, but you understand better. There is one thing I realized when you can explain something, people, when you explain people in terms of either food or in terms of some kind of fighting and violence, people understand really well. So there was some concept, I don't remember what it was. I was trying to explain words and all, nothing understood. I explained it in terms of pizza and everyone understood. I don't remember which one. So okay. Now for frequencies, right? Normally the device which we use is a tuning fork. So tuning fork is these things, right? They generate constant frequency. It doesn't matter how hard you hit it. You hit it gently, you hit it hard, it always generates the same frequency. Think of a simple pendulum. The time period of a simple pendulum is independent of amplitude, isn't it? Again, for small angles, whether you displace 1 degree or 2 degree or half degree, the time period will remain same. So tuning fork is one device which will always generate a constant frequency. So I'm pretty sure you must have seen a tuning fork. It looks something of this sort. So these things here are called prongs. So it will generate a frequency F. So if I take these points as A and B, the prongs, so whenever you oscillate a tuning fork, you know how it looks? So B is going this way and A is going this way. They always go opposite to each other. That means if I try to write the position of this thing, XB will be A sine omega t. They actually oscillate in SHM. This A is at the mean position, but going in the opposite direction, omega t plus phi. So both the prongs will always oscillate out of phase by pi. That means same thing when they're coming inside. A is coming in and B is coming this way. Now, how can you mess up this frequency? Normally you can't, but if you add weights, maybe you can put some weight, or generally people use wax also. If you take a candle and rub against it, the wax will get deposited, so weight will increase. Wax is easy to remove also. Heat it a little melt off. So the frequency decreases because it becomes more difficult for the prongs to oscillate. Another thing you can do, you can increase the temperature. If you increase the temperature, the prongs become a little longer. It becomes more difficult to oscillate. So if you increase the temperature, even then frequency decreases. There, if you want to mess up the frequency, this is what you can do.
Can we do that? I was filming that. Hello, internet.
So there, the guy is holding a tuning fork.
Sounds like a in water. Oh yeah. So I have some choices for you, Dan. Do you think it will look A, really awesome? Really awesome. Right.
So that thing has a frequency of around 1600 hertz. So what they're going to do, they're going to hit it and put it on a water surface.
Yeah, let's go.
Whoa.
Let's see that in slow motion.
It's like the smallest little bit of space in the world.
Oh, that's severe.
Oh my god.
Might have been over exaggeration. Alright.
Can you see how the prongs are vibrating? Look at this.
Alright.
See how they're going. They're going away, they're coming in. They're going away, they're coming in. And when they hit the water surface, notice something here. Did you see the glass cup bowl surface tension? The edges of the water are actually curved. And when they pull out, you see something even more interesting. You actually see the contact angle. Capillary action. Can you see how the water is being pulled up? The water is sticking to the prongs actually, the contact angle. And not only that, see when the water drops, see how that surface behaves. It behaves like a membrane. The water just doesn't get mixed up. It actually floats on that surface. It's actually a better video for surface tension.
YouTube.
But anyway, that's a little bit about the tuning fork. And look at this thing. I'll post the videos in the group anyway. I think there's a little lag. There, that's a slinky. Now see, when you move it, that thing is going up and down, but you can see the wave is traveling forward. And if you see, almost that point is at the same, it's on the, not going left and right. This would be your transverse wave.
Hi guys, today I just want to show you so you can see. Let me give this a go.
Same thing, yes. This is again transverse wave.
So
You can see the pulse how it is going like a snake.
Are moving from the left to the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular.
The other way around.
So is going to be, or the medium, the slinky is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave.
Can you see how the pulses are traveling? If I pause it, can you see that pulse? This is the compression. It goes forward, you can see the compression is coming. One more compression is coming. Another compression is coming. So you can see how the compressions are traveling forward. Here the wave is also going forward,
So
the compressions are also going forward.
There's
That is the
part
longitudinal
where the
wave.
wave gets compressed, and a part where the
So that's a bit about it. Play with this. Take a small break. Come back by 9:46. Any doubt so far? Chalo, let's start off. So how do you generate these waves using a tuning fork? Case one, let's say you keep the tuning fork vertical. And let's say you tie a string like this. So this is the scenario at t0. We know time period is equal to 1 by f, the frequency. So if I take t by 4, t by 2, 3t by 4, and t. So this a will go to the extreme position. So the initially it is at mean. So when this goes to the right, what will happen to the string? It will form a small bump here, a lower bump. Basically, you created half the wave. Then when you suddenly pull back, you get a thing like this. Then again, when it pulls back, again, I'm not drawing it exactly proper. And then finally you get a something of this sort. So if you connect the tuning fork vertically, every time this thing completes one oscillation, you actually generate two wave pulses. In one oscillation, we get two pulses. So wave frequency will be 2f. Right? But generally people don't connect like this. We do it the other way around. So case 2, you keep the tuning fork horizontal. So the position of the tuning fork itself will mess up your frequency. You have to be careful. So at t by 4, it will go up. So the pulse will be like this. You created basically 1/4 of the wave. When it comes down, you get a bump like this. Then something of this sort. There. So basically you create one full wave pulse. So for one oscillation of the tuning fork, you get one wave pulse. So in this case, the wave frequency will be equal to the frequency of the tuning fork. So remember, if nothing is mentioned, we take this case. With the tuning fork, you can actually generate two different frequencies. So if they simply say a tuning fork is used to generate a wave, we will always assume this case. Unless specified, don't take case 1. But that can be a good theoretical question. Play with this. That's about the frequency. That's your first property. The second property is the wave speed. So wave speed is nothing but it tells you how fast is the disturbance propagating. the speed at which wave propagates. Now this wave speed is independent of the source and depends on the medium. That means whether you shout or I shout, the speed of sound will not change. So basically how fast that disturbance travels will depend on the elasticity of the medium. We will see later on it depends on the bulk modulus. If the molecules are more closely packed, the disturbance can travel faster. So it depends on the medium and independent of the source. It doesn't matter who created the disturbance because the disturbance was created in the medium. So it depends on the medium. So here's one thing you have to be careful. So when you talk about a wave, there are actually two different speeds here. If you just look at this point A, so after some time, if you see A is actually going up, this is called particle speed. So don't get confused. So particle speed is different from wave speed. Wave speed is simply how fast is the wave propagating, how fast is the disturbance traveling. Particle speed is the speed at which the particles are moving during the wave propagation. So wave speed and particle speed are two different quantities. Yeah. The third thing is your amplitude. This is the same thing that you learned in SHM. Maximum displacement from the mean position. Again, this thing also, this depends on the source and the medium. Did you ever do that battle rope in the gym? Or ever seen that ad or something? Gym mein hota hai na, you take that big rope and you do up and down like this. So if you see, if you jump very high and do it, you get a big, wave. So it depends on the source, how much amplitude you can get. But if you make the rope too thick, you can't get too much amplitude. So it actually depends on the medium also. It depends on the source also. So frequency didn't depend on the medium, it was depending on the source. Wave speed depended on the medium and didn't depend on the source. This depends on both. So if you have a rod or something like this, and let's say this is oscillating y is equal to some a sine omega t. And for this guy, if you connect a string, you generated a wave. This is just like the battle rope. Think of this rod as your hand. When you're moving your hand up and down, the string also starts oscillating. So normally amplitude of the source becomes the amplitude of the wave, generally. Clear. So till now we saw the definition of the wave, then we saw the types of waves, and then we saw the three properties to study the waves. All great, completely theoretical. But then again, in science, right, always, if you can't represent something in a mathematical form, if you can't quantify things, then you can't use it for any practical applications. Just knowing what is a wave and properties of a wave will not be of any practical application. Anytime in science, right, if you can't measure stuff and you can't put it in a mathematical form, you can't calculate the precise values. For example, when you want to do a rocket launch, we know the concept of rocket, right? Gases will come outside, rocket will go forward. But with this calculation, you can't launch rockets. You need calculations, you need exact how much weight you're sending, what, and blah, 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 everything. So we need to represent a wave mathematically. So wave equation. So that's what happens when you take science, right? As you keep going, at some point, max will be there. If you can't put that in the end of the mathematical terms, it is of no use, no matter how much you study theoretically. So in a wave equation, so what are we studying exactly? Let's go back to the basic. What is a wave? We said wave is nothing but propagation of a disturbance. What is a disturbance again? The change in property. So what we are studying is the change in property. So we represent y, which is the property. Now this can be anything. It can be displacement, it can be y coordinate. It could be density. It could be pressure. It could be magnetic field or electric field, anything. But for our understanding and simplicity, let's take the wave on a string, because that is something which we can easily visualize. So let's say I'm putting a y-x graph. So y-x is simply the photograph basically. Let's say you have a string. This is the pulse. Y is equal to f of x. So what is this thing giving you? So this is basically giving you the height of the particle on the string for every x coordinate. For example, say x is equal to 5, let's say height is 2 millimeter. X is equal to 4, height is 3 millimeter. X is equal to 1, height is 6 millimeter. X is equal to 0, height is 8 millimeter. So these are different heights of the string. Basically, this is that bump. So on a string, you generated a pulse, and y is equal to f of x, where y is the height of the particle and x is the x coordinate of that particular particle. And let's say this bump is traveling with the speed of v wave. This point is 0, 0. This height will be f of 0. And this is the scenario at t is equal to 0. So after time t, this bump is going to travel forward. Your picture will become like this. The bump has gone ahead. That means this bump ka peak value has traveled a distance of vt, 0. But we know this should be f of 0 again. So what are we doing exactly? Shifting of origin, isn't it? So you're shifting the origin from 0, 0 to vt, 0. Think about it. If I still write here f of x, and if I put x is equal to vt, will I get f of 0? So when I put x is equal to vt, I should get 0. मतलब यहाँ पे equation क्या होना चाहिए? The equation must have become y is equal to f of x minus vt, isn't it? Basically, you have shifted the origin from 0, 0 to vt, 0. And when you shift the origin, what you do? You subtract vt from everyone. So I subtract vt from x. So y is equal to f of x becomes y is equal to f of x minus vt. So there, we have created an equation which is depending on position and time. We will talk about that. But so if you have an equation in this form, this is called a right traveling wave. So after time t, this bump will travel a distance of vt. Since the peak value still has to be 0, so what you're trying to do is make this into a new origin. So vt, 0 must become the new origin. Similarly, if this bump travels to the left-hand side, then this will become minus vt, 0. That means your wave equation here becomes y is equal to f of x plus vt. So this is your left traveling wave. So the plus and minus in the middle will tell you which way the wave is traveling. So if I combine these two, we can generalize the equation. Y is equal to f of x plus or minus vt. There, this is the mathematical form of a wave. Again, what do you mean by that? Ask yourself, what is y? So indirectly what you're telling is y is a property that changes with x and t. Meaning, let me give an analogy. Think of like this. Let's say here y, now all of you are there. Let's say I'll define something arbitrary. Y is the displacement of your right hand ka thumb. Y is the displacement of your right hand ka thumb. Now, if I ask you this question, what is the displacement of the thumb? What is the first thing you will ask? Sir, whose thumb are you talking about? There are 20 people in the class. Whose thumb am I talking about? So I need to define your position, isn't it? So let's say I defined, okay, so and so person. Next thing, what time you want the position of the thumb? Are you asking right now? Are you going to ask 1 minute later or 1 minute back? Are you getting this? So if I want the exact position of a thumb, I need to tell you two things. One, whose thumb am I talking about? Second, at what time are you asking, isn't it? Without giving these two informations, what I'm asking is invalid. I'm just asking something arbitrary. Now, the same story, think about this. When I'm sending this wave pulse, this wave is continuously going up and down. So when I ask you displacement of the particle, what should I tell you? Which particle are you talking about? You're talking about this particle. What time you're talking about? Isn't it? Because after some time, what will happen? This pulse will go forward. This particle will look at this point here. When we did this example, if I ask you, let's say there are multiple points here, A, B, C, D, E. Now, if I ask you, find the displacement of whom? You want the displacement of A, B, C, D, whom? Tell na, that is your X. Second thing, okay, I'll say it is for A. What time? This one, this one, this one, this one. Which one are you asking? Are you getting? So basically, whenever you're studying in a wave, you're studying the property. Great. But that property will depend on which position you're talking about and which at what time. So a wave equation is actually a two variable function. Till now, we studied every time, right? In only one variable, velocity as function of time t, velocity as function of position, acceleration in time t. Getting it? So this is the, I think, first time we are seeing a function where it depends on two variables. Actually not new. If you remember, PV is equal to nRT, this pressure is equal to NT by V, it depended on three variables: number of moles, temperature, and volume. But there also, you know what we did? Whenever we studied graphs, we kept volume constant and we said pre-proportional to T, isn't it? You always used to keep two constant and study one variable. But are you getting this thing? So this can be written as this. You can also write as f of ax plus or minus bt. Same thing. Plus indicates right traveling. Minus indicates left traveling. And we define something called a progressive wave. So progressive wave is a wave which keeps going in one direction. Basically, it never turns back. So this is the equation of a progressive wave. Basically, you can see that the bump is always going in one direction. Don't worry, we'll see more about this equation. It's like max mein this hai na, what is the equation of a curve? Y is equal to f of x. But what do you mean by y is equal to f of x? It can be y is equal to x square, y is equal to x cube, isn't it? It's a function of x. So this is also the same thing. He's saying the property is depending as a function of x and t. That property can be magnetic field, electric field. If you remember last class, I gave an example. Do you guys remember this equation? I said magnetic field is sine kx minus omega t. अभी दिख रहा है कैसा है वो equation? It looks like x minus vt ना? So that is also a wave. So you will see it has a different forms for it. Now the problem again here is we have two variables, x and t both are changing. So how do we study this? I can't have both the variables. Now let's say if I keep time constant. Can you tell me if I keep time constant, what am I looking at? Again, let's go back to our Tamga example. So if I'm looking at all of you, if I'm looking at all of you at the same time, what am I looking at? A photograph, isn't it? Positive is for, yeah, I wrote wrong, sorry. This is minus and this is plus. What am I looking at? A photograph, isn't it? You know, even your vision is something like this. Now, you're looking at the screen, right? Try to do one thing. Try to look ahead, try to look at your screen, try to look at the wall, try to look at the entire thing in front of you. When you try to do that, you can look at the whole thing, but you can't focus on any one thing, isn't it? Now you try to focus on the screen. You can see the screen, but you can't see anything beside that. So if we see our human vision, right, we have two types of vision, a wide vision and a focused vision. When you use one, you can't see the other one. If you try to focus what is in front of you, the other things on the side background goes off. If you try to see the whole thing, you know what happens? If something is moving here, you know something is moving, but you can't tell what is moving. Generally, people use this while driving. You're going on a road and you're having a wide vision. You're getting it. If something comes from the side, you exactly don't know what is coming, then you focus on it. Getting it? So something like that. So if you keep time constant, you know what you're doing? We are looking at all the points at the same time. Basically, you're looking at a photograph. So if you want to look at all your faces at the same time, now see, if I try to look at all your faces at the same time, I can't see. When I see one, the other guy's face has already changed position. So how do I look at all of you at the same time? Take a photograph and then see all of them, no? So we are looking at all points at same time. So that means, unfortunately, we humans cannot see all the points at all times. Either you can look at everyone at one time, or you can look at one guy for every time. Basically, it's a photograph. So in waves, whenever they give a graph of yx, they are giving actually a photograph. So if someone tells this is a yx graph of a wave, and let's say this is A, this is B, this is C. That means after some time, A has come here, B has gone up, C has gone again here. So if this is the position at t is equal to 0, this is the position at t is equal to t by 4. Can you see what is happening? The particles are moving up and down. So the photograph changes. So this is the photograph of the wave at t is 0. This is the photograph at t is equal to t by 4. So whenever someone gives you a graph, yx graph, it's actually a snapshot. So yx graph is a snapshot or a photograph. Clear with this? What happens if you keep x constant? If you keep x constant, that means we're looking at only one person for all times. Basically, you're studying the motion of one particle. So again, if you look at that example, so when the wave pulse is going, if you look at point A is only going up and down. So when they give you a graph, they're actually giving you the displacement of A with respect to time. So this is actually a graph. So YT graph is actually a proper graph. Clear with this? So YX is a photograph, YT is a graph. It tells you the displacement of the particle with time. This is the problem when you have two variables. You have one property depending on two variables. We can't see both at the same time. So unfortunately, you have to study one at a time. Either you study the photograph or you study only one particle. You can't do both at the same time. Clear with this? Great. So we got a wave equation, but a wave equation, only this condition is not sufficient. So for any equation to be a wave equation, it has to satisfy three conditions. The first one, it should be in the form of y is equal to f of ax plus or minus bt. We derived this. So you can actually write this thing as f is equal to, take out a common, x plus or minus b by at. So using this, we can define v wave is coefficient of time by coefficient of x. Which is b by a. That will be a proper CET level question. Example, they will give you something of this sort. They will say y is equal to e power minus 2x minus 3t whole square. This is actually a wave equation. So generally people think wave matlab sirf sine cos hona chahiye, not necessary. In our portion we have only sine and cos, but a wave equation can be anything. So here if they ask you the wave speed, so coefficient of time is 3 and by 2. The minus indicates it's a right traveling wave. So the plus and minus, suppose if there's a plus in the middle, then this is a left traveling wave, basically minus I cap. The plus and minus will simply tell you the direction. Magnitude is 3 by 2. 3 by 2 meters per second, or whatever, centimeter per second, depends on the unit. So if I give you a wave equation, I can tell you the wave speed from just looking at the equation. So first of all, it should look like this. This is the first condition. And that is what we derived also, if you see. Clear with this? Second thing. For example, if you take f of x minus vt, because there are two variables, when I differentiate, I need to do partial differentiation. If I do dou v by dou t, this will be minus v, f dash x minus vt, chain rule. If I differentiate again, I get dou square y by dou t square is equal to v square f double dash x minus vt. If I do the same thing with dou y by dou x, that will be f dash x minus vt. Dou square y by dou x square, that will be f double dash x minus vt. Now here, if I combine these two, the first ones, we get a pretty neat result. Dou y by dou t is equal to minus v wave dou y by dou x. What is dou y by dou t? Y is the displacement of the particle. So this is actually velocity of the particle. There, this gives you the relation between particle speed and wave speed. Quite an important formula. Most people ignore this, but a pretty good one. Because we kept on saying particle speed, wave speed, particle speed, wave speed. What is the relation? But there is a relation between them. This gives you the relation between them. And if you take the double differentials, we'll get d square y by dt square. That's actually kind of like acceleration. Vy square is equal to dou square y by dou x square. There is no, as such, no meaning of this. But technically, what this thing is trying to tell you is, again, a partially is not a complete meaning, but this means the function should be continuous and differentiable. You can think of like that. Think of it like this. If a wave equation is discontinuous, means what? You have a wave, suddenly it disappears and appears from here, right? In real life, can you have waves just disappearing and appearing out of nowhere? So it has to be a continuous function. Second thing, can you have functions like this? At this point, there are two velocities. In real life, can a particle have two velocities? So undefined. So it should be differentiable. It should, acceleration should be defined. Velocity should be defined. It should not be continuous. So to take care of all of that, if something is double differentiable, means all that is taken care. So you can think of like this. So instead of looking at this and getting scared, understand what it's trying to tell you. The function is simply telling you, boss, function should be continuous and differentiable. But sometimes when you see equation and you're not getting an idea what to do, this is the final proof. If you can prove this, means it's a wave equation. But happens rarely. Function should be continuous and differential. Most of the times you can see and figure out. We'll do a few things. But the meaning of this is that it is telling you, boss, a wave equation can't break. It should be differentiable. Velocity and acceleration should be defined. The third condition, the function should be bounded. Meaning it should not go to infinity for any value of x and t. Even if I put x infinity, the value should not go to infinity. So finite for all x and t. It must be a bounded function. There, if anything satisfies these three conditions, then it is a wave equation. Clear with this? Now I'll give you some functions. Now you tell me whether they are a wave equation or not. And if they're not a wave equation, which condition they don't satisfy. Any doubt so far? Which of the following is a there, 10 of them. Which of the following is a wave equation? If they're not a wave equation, then which condition they didn't satisfy? Try. I'll give an out. Exam, they'll give you 4 options and they'll ask you to find a wave. So don't think wave matlab har bar sine hoga. But sine is actually a very special type of waves. Let's see. First one, is it a wave equation? Nope. Q, it's not bounded. Because if x tends to infinity or t tends to infinity, then y tends to infinity. It doesn't satisfy the bounded condition, not be infinity. What about the second one? Sine is bounded. Third is fine. Fourth is gone. Tan 90 undefined. Fifth is interesting. It looks like x plus vt and x minus vt. Now, one thing I'll tell you, see, when you say something looks like x plus vt, it means this. If I replace x plus vt with z, I should not see x and t anywhere. Isn't that the meaning of it? The whole x plus vt is a variable. If you replace that with one variable, I should not see x and t anywhere. You'll have x plus vt and x minus vt. You can't have both. Are you getting it? Because see, sine a plus b, there is a formula. Is there any formula for sine ab? You can't split it, isn't it? So this is actually not, it doesn't satisfy the first one. You cannot have both. This is the kind of a question where you get confused now, then you do the double differential. You'll not get satisfied. It's a good one. We cannot have both. But another simple explanation is this. If you replace x minus vt with z, you should not see x and t in the function. If you see, matlab, it is not a wave equation. We cannot have x plus vt and x minus vt in the same function. F also denominator can go to 0. This is acceptable. E power infinity, it can be unbounded. This is acceptable. Non-zero undefined. Clear? So this y can go to infinity. X tends to infinity, y tends to infinity. Ln 0 undefined. If you look at the I, na, I is a good one, see. This minus sign and this square saved it. Because this is always a positive number and minus sign will always put you in the denominator. So e power minus infinity becomes 0. The reason this thing got messed up is because of that. Negative numbers are okay, but positive numbers will bound, it will become unbounded. Clear with this? So every time, right? That's what I'm saying. Only the sine function, look at this thing. This is also a wave function. These are waves. So a wave equation can be in any way. But again, in our portion, we'll limit our study to only SHM waves. So that is waves produced by sinusoidal sources. Clear with this? Any doubts on this? Anything that you're not clear here? Let's see one more question. Let's say y is equal to 5 by 2 plus 3x plus 2t whole square. Find the amplitude. Wave speed. And plot yx graph at t is equal to 3 seconds. Let's see how we do this. Let's see. Yeah, it is more of a max actually. So let's try to plot this graph at t0. You will see from there. So at t0, what will the equation look like? This will become y is equal to 5 by 2 plus 3x whole square. That means if you look at this thing, at x is equal to 0, you actually get the maximum value. And as x tends to infinity, y will tend to 0 and y will tend to. Isn't this how it looks? It's a bump in the middle. And what is the highest value of this bump when x and t is 0? So if x is 0 and t is 0, y is maximum. That is your amplitude. And therefore, amplitude is 5 by 2. That is the height of this bump, 0, 5 by 2. And what is the wave speed? Wave speed is coefficient of t by this thing, 2 by 3. And it is going left side, minus I cap. It's a left traveling wave. So this bump is traveling with a speed of 2 by 3 meters per second. And you're asking to draw the graph at t is equal to 3 seconds. So in 3 seconds, this bump will travel how much? 2 meters. The bump will look the same. This coordinates will become minus 2, 0, and this will become minus 2, 5 by 2. There, this is the shape of the bump after 2 seconds. 3 seconds. Clear with this? Coefficient of time by coefficient of x. Look at the dimensions now. Coefficient of time will be 1 by t ka dimension. X ka dimension will be 1 by x ka dimension. Clear with this? There, you can get questions of this sort also. Every time it won't be a sine function for you. So that is about your non-standard waves. So the next thing would be we will see like, the standard waves. In our portion, we have only waves which are generated by sinusoidal sources. That means you'll get all waves in forms of sine and cos. So those are our general wave equations, which we'll see in the next class. So next class when we catch up, we will continue from here. We will see the general wave equation, and then we will talk about wave speed and all that stuff. So we will see how to calculate the wave speed. Okay, so that would be the last one for the day. We have finished with AC and EMI. Again, I'm telling you, take time till next Friday, take a week's time and finish off AC and EMI completely and do it properly. Waves, it's an easy chapter. Matlab, if you actually understood the basics, and wherever it is possible, I'll try to show you as many videos as possible for understanding. The main thing is that only. If you understand, it's pretty straightforward. Okay, with that, we'll wrap up for the day, right? And I'll see you guys again on Monday as usual. So any doubts, anything, please stay back and ask, or else you're free to leave. So take care, stay safe.